Okay, so now let's move on to apply the technique of gradient descent to linear regression with multiple variables. And you'll see it's very similar to linear regression with a single variable. And the matrix notation will help us enormously. Right? If you recall, when we did univariate linear regression, our cost function, which we sought to minimize, had this form. It was the sum over all rows in the data table of the prediction minus the actual value squared, and then divide by 1 over 2m. So it's actually 1/2 the average squared error. Okay. So we also had this gradient descent formula that theta was updated by basically going downhill, right? You took your previous theta, you evaluate the derivative of the cost function, which tells you the downhill direction, and then you move in the downhill direction by an amount proportional to alpha, which is called the learning rate. So you can go back and review that video, and you'll see that we'll be using the same concepts here. Okay, so here we have our x. Remember, our x, we're representing that as a column vector, and theta we're also representing as a column vector. Now, be careful here. xi in the table is a row. So this is one row of the table, but we represent it as a column vector. Right? Let's move on. All right. So, what do we do here? There's only a very slight change from univariate regression to multivariate regression. Right? Previously, we updated theta 0 and theta 1 using this schema. And remember, this inside the summation turns out to be the derivative of the cost function with respect to theta 0. This is the derivative of the cost function with respect to theta 1. We use the same template for all of the thetas, and you can see that this is very consistent. Now, see here, he actually multiplies this by theta 0 here, and there's no theta 0 here, excess theta 0. In fact, all the formulas here for multivariate regression are identical to the formulas here. I just replaced the subscript. For instance, at the subscript 1 here, I replaced this subscript with subscript n to get the nth component of the feature. One difference is you can see here there's this x sub 0i, and here that doesn't appear here. But in fact, it does appear here, because remember that x sub 0 is actually equal to 1. So expressed in this way, we can see the consistency of all these equations that determine the updates of the coefficients in our linear regression. Right? And so that way we'll be able to treat them in a uniform or unified way all together using matrix multiplication. Right? So let's see. All right, so we're given x. So that went by quickly. All right, so we have our feature vectors. We can write them out as components. We have our theta. We have our y. We have our matrix equation that expresses our prediction, right? And we want this h theta of x to be as close as possible to the y vector that we can make it, right? So the updates to all the thetas can be made simultaneously using the following equation. Theta is theta minus alpha over m times x transpose times x theta minus y. If you look back at the previous equation that we had on the previous slide, let's see if we can go back there. That's exactly what we have here. Notice we have the x's inner product with these values here. Now take a good look at this equation. What's going on here? Well, you have the theta and the minus here. You have alpha over m. That looks familiar. Now, x transpose times x theta minus y. This x theta minus y is a single column vector. That represents the difference between our predictions and the actual value. So each row will have a prediction and actual value, and this is the column vector that represents those differences. Now, what does this X transpose mean? Well, what happens when you do this matrix multiplication is that each row of X transpose multiplies this same column vector. Think about how matrix multiplication works. It's row of the first times column of the second. Since this has only one column, we're multiplying each row of X transpose successively with this same column vector. First the first row, then the second row, then the third row. Now the rows of X transpose are simply the columns of the original matrix. So the first row of X transpose corresponds to the column that has the constant feature. The second row will correspond to the second column. Now, if you recall, the update equations deal with these columns one by one. Let's look back and see the explicit relationship between this and our previous equation. Okay, this is what we had before. So this was the first one, right? What are we doing here? We're taking this sum, which is actually giving me an inner product. Now, what is the inner product? Here you can see this vector here. This vector is the prediction minus the actual value. So this is the error vector. And you're taking the inner product of that with this. Now, what is this? This is the first column of my data matrix. So it's actually the transpose of this column vector times this column vector. Right? The transpose of this column vector is a row vector. This is actually row vector times column vector. Right? And here we see the alpha and the 1 over m. So I would suggest you flip back and forth between this set of equations and this matrix representation here until you see that these really are the very same thing. This is a much more elegant expression of the same set of equations. Now, the cost function is also a sum of squares. So it's a sum of terms, and this can be considered as an inner product of the error vector with itself. Let's go back to the cost function expression and see how that works. We'll see that it is actually an inner product. Here you have the cost function from our previous slide. It's the sum of m terms, where each term is a square, and this is the ith component of the error vector. So you're multiplying the ith component of the error vector with itself and summing over all of the components. So in fact, it's an inner product of this vector, this error vector, with itself. So I can write it as the error vector transpose times the error vector. Okay, let's continue. Now, when you do linear regression in practice, you actually don't deal with any of these equations because it's done for you in Python. Now, this is one implementation of linear regression in scikit-learn. There are others as well. And you do need to be careful that you set up your model correctly. Some implementations ask you to add the column of ones and some don't. So you need to look at the documentation. For the linear model in scikit-learn, you don't need to add the column of ones or the constant column, and it will produce a model for you. So the specifics of how to do this we can go in later, but all of this under the hood is what we've just seen. So now you know what's going on in this module here. Okay, so that's it for this video. We'll talk about more practical tips in the next video.